Hello everyone, my name is Kyle Wendy and I'm the Chromatography Application Scientist at JASCO North America. Thank you so much for joining our webinar titled The Importance and Evolution of Chiral Nicotinoid Separations. Today our speaker is Dr. Daniel W. Armstrong. Daniel W. Armstrong is the Welsh Distinguished Professor of Chemistry and Biochemistry at the University of Texas at Arlington. He has over 800 publications and received over 35 awards for teaching and research, including numerous ACS awards and the Chirality Medal. He has been named one of the top 10 analytical scientists in the world by Analytical Scientist magazine and was elected to the National Academy of Inventors in 2014. He has mentored and graduated over 120 PhD analytical chemists, nearly half of which were women. Dr. Armstrong developed the most comprehensive solvation and characterization models for room temperature ionic liquids and pioneered their use in analytical chemistry. He also developed ionic liquids as the most versatile mass spectrometry reagents. His work and columns were in part responsible for the chromatography-led revolution in chiral separations and provided the impetus for the FDA's regulatory changes regarding chiral drug development in 1992. He has developed rapid, high-efficiency microfluidic methods for analyzing microorganisms. His work has been cited over 53,000 times, and he has a Hirsch index rating of 116. He has organized many international conferences and over 100 short courses worldwide. Without further ado, I would like to welcome Dr. Daniel W. Armstrong.
Welcome. Today's talk is on the importance and evolution of chiral nicotinoid separations. Let's start off by looking at the structure of nicotine itself. Nicotine is chiral. It exists as enantiomers, as do most of the nicotinoid compounds. The dominant enantiomer in plants is the S- nicotine, shown here on the right. On the left, we have the minor enantiomer in most products, which is the R+ nicotine. Interestingly, many plants contain nicotine, in addition to tobacco, which contains the most nicotine at 0.5 to 3%. Plants of the nightshade family, such as eggplant, potatoes, tomatoes, green peppers, and cauliflower, also contain small amounts of nicotine, as does tea. Now, eggplant, interestingly, contains more nicotine than any other vegetable at 100 micrograms per gram. So if you go to your nice Italian restaurant and order an eggplant parmesan and a nice red wine and have an extra helping, you'll feel particularly good after that meal. Nicotine has a variety of uses. Obviously, it's well known that it's a recreational drug, particularly with vaping. We have to keep in mind that it's a stimulant that triggers the release of neurotransmitters, and we have to keep in mind that it is addictive. It is used in smoking cessation therapy, something we'll talk about a little bit later. It may possibly have mild therapeutic benefits in some neurological diseases and in managing those symptoms of such things as ADHD, schizophrenia, depression, but much more research needs to be done in these areas. Always remember, it's a stimulant, a vasoconstrictor, it raises heart rate, and it raises blood pressure. Now, nicotine has been used for years, since 1690 even, as an effective, very effective insecticide. It was recently banned in the EU since 2009 and then banned in the United States since 2014, mainly because it was not wanted as a residue on food crops. So what do we use today? We use neonicotinoids, things that are related to nicotine and been synthetically modified like imidacloprid, and these are used instead, although I'm not sure we want these as residues on our food crops either. Let's take a look at the ionization states of nicotine. If you put it in solution at different pHs, it can exist in three forms: as the free base, which you see on the left, as the monoprotonated form, and the diprotonated form. You have to go to a very low pH to get an appreciable amount of the diprotonated form. But the pH will govern what ionization state the nicotine is. Let's also take a look at other tobacco nicotinoids, because in tobacco you have not only nicotine and its enantiomer, you have anatabine, you have anabasine, and you have nornicotine. All of these are chiral as well. Interestingly, anatabine has been used as a dietary supplement. It's been studied in a lot of animal models to see if it might be useful in treating nicotine addiction. But it seems to have an interesting effect in inflammation, anti-inflammation. It's been studied in models of diseases characterized by inflammation, including Alzheimer's disease, multiple sclerosis, and so forth. And anatabine cream was useful in managing mild to moderate rosacea. Now, anabasine is a similar structure to anatabine, except it has no double bond in this particular location in the six-membered ring. Anabasine was previously used as an insecticide. It's the dominant alkaloid in some plants, including one called tree tobacco. The tree tobacco leaves are sometimes mistaken for wild spinach, which if eaten can be fatal. Anabasine is considered more toxic to many mammals than nicotine. It's also a clinical biomarker for exposure to tobacco smoke. Nornicotine has interesting effects as well. Some research indicates that it might be useful in pain mitigation, such as in neuropathic pain. A recent study indicates it may mitigate weight gain. But you have to keep in mind it's a precursor of N-nitroso-nornicotine, and this is produced when you cure and process tobacco. Nornicotine can also react with human saliva to form N-nitroso-nornicotine, and this is a type 1 carcinogen. Now, the connection between smoking and cancer is indisputable and well known, but smoking is also a risk factor for developing Alzheimer's disease. However, there's some indication that the application of transdermal nicotine patches can improve cognitive performance in those with mild cognitive impairment, which is a condition that precedes Alzheimer's disease, but more research is needed in this particular area. Nicotine acetylcholine receptors in the brain are involved in memory, attention, and other cognitive processes. So there is a biochemical connection here. There have been many reported methods to analyze nicotine and nicotinoid enantiomers, and these are listed here and have been reviewed recently. Polarimetry, an age-old technique, can be used to distinguish between S and R nicotine. They're characterized by, in the case of the S- nicotine, minus 163 degrees, and alpha D, and plus 169 degrees, respectively. This method is insensitive and it requires very concentrated samples, and it's affected by impurities, so it's not a popular way to analyze enantiomeric composition. NMR has been reported as a possible method. It also requires somewhat more concentrated samples. Also, you must have chiral lanthanide shift reagents or other chiral complexation reagents. C13 NMR is thought to be a little more favorable than proton NMR. The technique also can be affected by impurities. GC has been reported in a few cases for the analysis of nicotine and nicotine analogs, but you have to remember that these compounds must be derivatized to enhance their volatility or to make diastereomeric derivatives. The STAR method is, of course, liquid chromatography, HPLC. It's far and away the most popular and effective way to analyze nicotinic compounds. It requires the least sample prep, and it's effective for the broadest range of compounds if you use the right column, something we're going to talk about. Furthermore, you can use UV detection, you can use circular dichroism detection, or mass spectrometry detection, and we'll give examples of this in a little bit. A little bit of history. What's the first reported nicotine enantiomeric separation? That occurred, I believe, in 1987, and here you see the separation of nicotine and benzyl nornicotine. Note that it took 4 hours in this case to obtain the separations. It was a 1 meter microcolumn, and the mobile phase was a saturated solution of beta-cyclodextrin with an acetonitrile water mobile phase. So you did get a separation, but not many people wanted to wait 4 hours. Now, also about this time, a new beta-cyclodextrin bonded phase came out and was marketed commercially. When that was used, the nicotinoid compounds separated quite well, except for nicotine. Nicotine itself did not separate, but the other compounds did much better. One interesting note about this particular paper is illustrated by this figure, which is a plot of retention factor versus acetonitrile concentration. This plot has a minima, and notice as you go to higher acetonitrile concentrations, the retention increases and the enantiomeric separation is obtained. What's interesting about this is a helix separation. This is one among many publications that we and others published years before the term helix was invented. Also in 1989, we published the correct mechanism for helix. The first gas chromatographic separation of nicotinoids independently, but not for nicotine once again, was in 1990. Here you see anabasine, 4-methylnornicotine, and so forth. Note that you have to derivatize them, in this case with trifluoroacetic anhydride to derivatize the amine functional group, and you could get a separation. But it was evident that this approach was not really competitive with HPLC, as the compounds had to be derivatized for volatility reasons or to enhance enantioselectivity, and it also seemed to be less broadly enantioselective. The first somewhat effective HPLC method for nicotine was a derivatized cellulosic chiral stationary phase, and you see the separation here to the right. But this is another example of how you analyze nicotine in other products, whether it's tobacco products or nicotinic patches or gum, which is first on the left you have to isolate the nicotine, which is peak 1 on a non-chiral separation. You isolate that compound and then you switch it to your chiral column where you get your enantiomeric separation of the S- nicotine and the R+. And it's a reasonable separation, but the minor enantiomer is coming out on the tail of the major enantiomer. So it could be improved upon. This slide shows the enantiomeric purity of nicotine that you buy as chemical reagents. And it doesn't matter what your source is, Sigma, Ulrich, Fluke, or any other company. It doesn't matter if you buy the plus enantiomer or the minus enantiomer of nicotine. The point is you will always find some amount of the minor enantiomer present, usually between 0.2 and 1.2% or so. And this shows you the relative amounts of the minor R plus nicotine in pharmaceutical formulations, whether it's a gum, patch, or in a nicotine nasal spray. You always find some amount of the minor enantiomers, the R plus enantiomer, once again in the range of about 0.2% to 1.2%. And here you see the relative amounts of the minor enantiomer, the R plus nicotine, in smokeless tobacco and unprocessed and unblended tobacco, whether it's a chewing tobacco, snuff, what have you. You will always find some amount of the minor enantiomer in that product. Then the big change came, the macrocyclic glycopeptide chiral stationary phases, which have very broad selectivity. The original vancomycin column, shown structurally on your left, was synthetically modified to become a superb chiral stationary phase for nicotine, and it was even given the name Nicoshell because of this, even though it separated far more than nicotine and nicotinoids. Plus, it was a core shell column, so it got very high efficiency, very low retention times, beautiful chromatography. The most comprehensive chiral separation paper on nicotinoid compounds ever reported was this Talanta paper in 2018. It shows the enantiomeric separation of 40 tobacco alkaloids and their tobacco-specific nitrosamine metabolites. It covered virtually everything you could possibly be interested in. In the upper left, you see a list of all the possible tobacco alkaloids. On the right, you see synthetic derivatives of the tobacco alkaloids. On the next slide, you see all the identified metabolites of the nicotine and the nicotinoids. And on the lower right, you see the tobacco-specific nitrosamines. These are the things that are capable of causing cancer. And here you see a typical separation on the NicoShell. On the top chromatogram, separation of S minus nicotine from R plus in 2 minutes. In case you think that's too long, below you see the separation of the same two, the S and the R, done in under 20 seconds on the NicoShell column. And you can use mass spec detection. On the left-hand side, we see 10 tobacco alkaloids. On the top, you see the total ion chromatogram. Below it, you see the extracted ion chromatogram of all 10 in the enantiomeric separation. In B, you see the 7 nicotine metabolites, the total ion chromatogram on the top, and the extracted ion chromatogram for all of them below. Now, in 2016, the Food and Drug Administration finalized a rule to regulate all tobacco products. And they said that for the first time, the Federal Food and Drug Administration, under the Federal Food, Drug, and Cosmetic Act, could regulate tobacco products. This was known as the deeming rule. Of course, this included vape and e-liquid products that initially used tobacco-derived nicotine. So tobacco-derived nicotine will be TDN. Then a small company came up with an interesting concept. They would synthetically produce nicotine. In this case, it was racemic nicotine, and it was commercially known as tobacco-free nicotine. Since it did not come from tobacco, it was not subject to the same regulation as all other tobacco-derived products because it wasn't a tobacco-derived product. So shortly after this, we did an evaluation of nicotine and tobacco-free nicotine commercial products, vaping and e-liquids. And here you see the separation that we use for the RNS nicotine, also for the nornicotine enantiomers. And here you see a typical separation. If you look at B, this is the UV chromatogram of a tobacco-free nicotine product. You see it has both enantiomers in equal composition. Lest there be any doubt, we used a JASCO circular dichroism detector. You see the negative peak for the S, the positive peak for the R. And you get the same thing for racemic nicotine standard. 2 peaks with the UV detector, negative peak for the S, positive peak for the R with the circular dichroism detector. We then proceeded to analyze a lot of nicotine in commercial tobacco products and in tobacco-free nicotine products. And I'm going to have you focus your attention on the bottom 5. These are the e-liquids. We'll skip the gums, the lozenges, and the various smokeless tobaccos and patches for the time being, and just focus on the e-liquids. And look at the concentrations of the first e-liquid, which is right here. It's a tobacco-derived product, claimed to have 24 milligrams per milliliter. We measured essentially 24 milligrams per milliliter. The enantiomeric ratio was at what you would expect, predominantly the S minus enantiomer with a small amount of the R plus. But then these new products that contain tobacco-free nicotine all claim to have 6 milligrams per milliliter as their concentration. But look over on the far right. These are the enantiomeric ratio. They're 50-50. So this 6 milligrams per milliliter was 3 milligrams of one enantiomer and 3 milligrams of the other enantiomer. Why is this a problem? Well, there's never been a comprehensive study on the pharmacological effects of the R plus nicotine, and yet you're getting 50% of that compound. And look at the experimental nicotine content. Sometimes 6 milligrams is what we found, 6 milligrams is what they claimed, But remember, this is 3 milligrams of each enantiomer. In other case, second from the bottom, 6 milligrams is what they claim. 12 milligrams is what's there. So I guess it's 6 milligrams of the S minus and 6 milligrams of the R plus, but it's not really said. Because this was obviously a huge problem and they had 5 years to get away with this, in 2022, the U.S. Congress passed a federal law allowing the FDA to regulate the tobacco-free nicotine products just as they did those that were derived from tobacco. You can also do supercritical fluid chiral separations of all the nicotinoids. Here you see them for anitabine, nicotine, anabasine, and nornicotine. Again, we use the NicoShell column. We use the JASCO model SFC 2000 for the SFC separations. And in these plots, we're just varying the amount of supercritical CO2 and seeing what provided the best enantiomeric separation. Green chemistry is all the rage, and you can have green chemistry for your nicotinoid separations too. You do it by calculating the analytical method greenness score for your analytical method, and how you do this is reported in this recent 2024 article. So if you want to do the greenest possible separations, it turns out they're SFC type of separations for anitabine, nicotine, and anabasine, using the NicoShell column and a JASCO SFC, and you get beautiful separations, and they're the greenest separations known for these particular compounds. For a technical note on SFC analysis of nicotine and e-liquids, I advise you to check this link, and the link gives you a nice outline of all the separations, the experimental methods, and so forth. So download this application if you have further interest in this area. Thank you for your attention.